Thank you very much. Welcome, everyone. I'm glad to see so many of you over here on this, maybe not a mainstream talk, but I will try to make it as interesting as I can. I come from Kraków. It's in southern Poland. I work at the university, and I really like Erlang. That's the reason I'm here. We are working with Erlang more and more, finding kind of new applications for it. I'm currently involved in the Paraphrase project, which is one of the European Union 7th program project ending next year. And I don't know how many of you is familiar with Paraphrase. This is a project about building design patterns for concurrent computation on multi-core architectures. So we will focus on building algorithms that work on multi-core, I mean really multi-core computers, not 8-core or 4-core as we have them now. We are lucky to test our solutions on 64-core machines, and later on we'll do it on supercomputers as well. So in this talk I will try to introduce you to agent-based evolutionary computing, which are two definitions I'll try to explain. This is the agenda, actually. I try to put it one under another, but it's hardly possible, so I made it a bit more complicated. Starting at actors, at processes, I will try to explain what are agents, what are they used for, what were they used for, what's the history of free-legged agent, why it can walk, and what's evolutionary computing, and getting from this to our implementation of agents in evolution, and later on to something that you are probably most interested in, which is application of Erlang in agent-based evolutionary computing. This is our task in Paraphrase, to test results of Paraphrase project in an application. This is a kind of computationally intensive subject, computationally intensive application, this evolutionary computing. We use agents to do it, this to solve particular computational problems. I will get into details a bit later. Okay, so starting at the very beginning and with a little of a history, just to introduce you to the agent paradigms. Everyone knows probably what is actor model, as this actor model is somehow considered a basis of Erlang processes and basis of Erlang concurrency model, which is not totally true, but to some extent. It defines an actor, a universal primitive, which can send messages, provided it knows the address of the actor, which can receive messages and react appropriately, and it can create more actors. It was proposed by Carl Hewitt back in '73, and well, further development of this model evolved over the years, but the basic assumptions remain the same. Actually, the model was a bit premature, you might say, at that moment. In Erlang, I will not explain you the details of Erlang because all of you probably know it. So you might say that those assumptions of actor model are very similar to what processes in Erlang do. There is almost a set of identical assumptions. Besides of that, actors do not assume single-threaded execution as processes in Erlang do. In Erlang, if you execute a single process, you have a single stream of instruction. An actor can be parallel in execution itself inside. Okay, so it was 1973 when the actor model was defined, and officially 1991 when the first Erlang was released, and the work started in 1985. Of course, later on the Erlang supremacy, and hopefully it will last for a long time after the symmetric multiprocessing was introduced to the EVM, and after multi-core processors were made popular, and more and more cores are becoming available. But what happened in between? What happened in the meantime? There was a model for computation, and actually there were some implementations, but all this time you could call a dark era of shared memory concurrency. This is the time where single-threaded CPUs were made faster and faster with faster clock, with smaller size and more and more transistors in it. So the shared memory concurrency was kind of sufficient for this model. Later, after introducing threads and multi-threading on a single core, it started showing big problems, and right now in multi-core architectures it is obviously insufficient. However, in these dark days, the universities were kind of carrying on with the ideas of actor model defined back in '73. Starting in '70s, even a little before the Carl Huey's first paper on actors, and in '80s, the theory of agent model of agent paradigm has been developed. This agent paradigm defined an agent as a universal primitive which the definition starts in a similar way as an actor, which is a computer system situated in some environment that is capable of flexible, autonomous action in order to meet its design objectives. You might say it's not very precise, and you will be perfectly correct saying that, because this is only one definition of agent systems, of agents. There were many other definitions, and those agents were never actually defined formally to one common definition. But many people worked on this idea of actors, of their further development, of further applications of this actor model to, well, variety of domains. To model interactions between autonomous beings, the multi-agent systems have been defined. These multi-agent systems, well, simply sets of agents that could coexist in some way. So the assumption was that these beings are independent. They do not share state. They do not share data. They do not have a global control system. They do not even share the aims of their existence. So each agent had own knowledge based on observation, whatever the observation was, and it had the ability to communicate with other agents with asynchronous messages, as in actor model. So a bit more added to actor model as in terms of aims, and a bit more like scientists like doing, make it more complex, it will be better. Different things were added to this model. Asynchronous computation, so we needed autonomy, and this autonomy of agents is probably the most common term for all the definitions of agents. Very huge amount of work was put into defining new versions of agent system, multi-agent system in different domains, in different applications, solving many quite complex problems, like, for instance, heterogeneous systems integration. The agents, back in the 80s, actually, were able to communicate between heterogeneous systems. So we had a virtual machine connecting different systems. Even with agents written in different technologies, these agents were able to communicate. That was one of the aims of the assumptions. Another thing was agents mobility. There were experiments with agents written in as a shell commands, and agents able of sending themselves to different computers over the network, executing some code over there, and finding way to move somewhere else. This included code and state migration. So you could imagine a code going to your resources, to your computational resources, to your data, with state to perform this computation more efficiently, and then go back. So this kind of stuff was considered interesting. Later on, the scientific world added even worse things to agents, like pieces of artificial intelligence. So knowledge representation, understanding and exchanging, and knowledge using. So basically the worst phase of AI. The ontologies. ability of understanding spoken language, written language of human beings, ability of communicating with human beings, of simulating behavior of human beings. At this point, this paradigm has become such a huge thing that it couldn't work. It couldn't be practically applied in any domain. So this created this three-legged creature with three basic assumptions. The conferences in 80s and 90s on agents were just divided into three parts, actually one after another. One was about model of computation, so the parallel or rather concurrent computation. One was about heterogeneous system integration, which was rather, and still is, rather important issue in distributed systems. There was even something, and still is, called Foundation for Intelligent Physical Agents, FIPA organization, which defines standards for agent communication. They managed to define standards of implementing protocols of communication, and over these protocols, a language, how agents should communicate one to another. So this was a huge amount of work to do this and to make it work. And later on, of course, this distributed artificial intelligence was all put all over it, and well, this creature couldn't walk very far. So actually, this is a shame that this amount of work somehow passed unnoticed. You can find this term of agent in different papers right now, used in many random situations. You can't even tell why this notion is used, but that's what was left. In the 90s, there were several quite good implementations of this agent paradigm, including FIPA standards, which mean that the agents in, let's say, Jade, which is the most popular agent platform, could even migrate with the code and with the state to a different node. There was a virtual Jade machine connecting heterogeneous nodes. Whichever computer could run Java, could run Jade, and it could be interconnected into one single virtual machine. And it was done. It was working very inefficiently. Only hundreds of agents could exist on a single node. Well, we actually made an experiment to show you how inefficient these implementations were. We compared some features of these platforms to Erlang, because we like Erlang. This is the first two-dimensional chart I will show you today. I'm from a university, so I have to have this kind of stuff in my presentation. Okay, so this is the creation time of agents compared to Erlang process creation time. The blue one is something called Magentix, the red one is Jade, and the Erlang is yellow. And this scale over here is not linear. Actually, both of them died about 1,000, below 1,000 agents. This is the limit of system threads you could start on this machine. We didn't tune JVM, we didn't tune Erlang virtual machine before this test, so that's the limit. And actually quite interesting how many processes we could start in Erlang. That's 1 million processes, still 0.002 seconds per process to start, so quite efficiently. That's what we like, right? Another test involved messaging. This is messaging on a single node, where in Java-based implementation you had, we didn't weight it above 1,000. You can see that the Jade implementation is rather correct because it doesn't depend on the number of agents. The Magentix implementation is as poor as it causes, it takes way longer if you have more agents. This doesn't make any sense. But this is the way it was implemented. And of course, in Erlang, again, you have several orders of magnitude better solutions. And even in a distributed configuration where you have up to 20 nodes, this was number of messages exchanged between randomly selected agents or processes on different nodes, and round-trip time measured. So as you can see, both Java-based implementations depend on the number of computers. So the bigger the cluster, the worse it works. And up to 20, the Erlang, well, kept pretty much the same. We know that there are some issues with really, really big clusters of Erlang, but we didn't have a chance to verify it. Basically, that was also not the point. Okay, and actually, there is one thing in common already done between Erlang and agents. This is called EXAT, Erlang Experimental Agent Tool. This is an agent framework, FIPA-compliant agent framework, implemented in Erlang. And it turned out that this implementation, which integrated some AI libraries and all the protocols defined by this FIPA organization, caused Erlang to work slow. So this is not probably the step into correct direction. So just to sum up this agent part, huge amount of work, huge amount of specification and implementation that really worked, which never, almost never, been applied in the industry, which is a shame because those standards were pretty good at that time. But the implementation was based on the JVM or sometimes C++, and the performance was simply not enough, and the huge problems with memory those platforms experienced just made it useless in industrial applications. Okay. Nevertheless, we like the assumptions of the paradigm. So the set of autonomous beings doing something on their own, being selfish, can be used to model some bio-inspired environments. As we, for instance, we're kind of selfish. We have our own aims. We have some common goal if we are organized, but we tend to do some things for ourselves. And it kind of works. So we didn't drop the idea, we dropped the implementations. And the idea of these agent systems can be successfully implemented and used in many different domains, like, for instance, the one I'm going to talk about today, which is evolutionary computation. I don't know how many of you are familiar with this idea, maybe with basics mostly. Yeah, okay, so just briefly tell you the story, what it is about. This is a group of computational intelligence method, that's they call, inspired by the mechanism of biological evolution. And they are suitable for solving some particular optimization problem. Not all optimization problem, but there are some more suited to particular optimization problem. I will focus on genetic algorithms today. Which is actually the last one you would use coming across a real-life problem. If the problem is as hard that you cannot think of any better method, any analytical solution, or any better heuristic to solve the problem, you can almost always use a genetic algorithm. So it is pretty much universal. Because of that, it is often used when it's not necessary, but because it's also very simple to implement, this is very, very popular in many domains. You can find implementations, I heard about implementation in Australia, in scheduling wine production, using this kind of algorithm, cutting glass, so that you can get as much as you can from a big sheet of glass, and things like this. I don't know, scheduling trains and planes and things, the different optimization problems. Okay, getting briefly through the classical version of this algorithm. You randomly select a set of solutions. You have to represent what a solution is. So for instance, if it's I don't know, finding a path from one node to another in a graph, this will be just a list of nodes getting from one place to another, and you're trying to find the shortest one, if you want something like this. Or this is simply the schedule of trains, one schedule of trains, and you want to somehow find out the best one for your needs. So you have this initial random set. Then you have the genetic operations that take this random set, or this set in next iteration, and somehow convert it, modify it, so that it can generate a new set. This new set can contain some solutions from the previous set and some new solutions. Some are removed. And repeat until some condition is met. For instance, a good enough solution is found. These methods are applied in situations where you actually don't know if you found the final best solution, because you have no way to determine if the solution is the best. You probably have a global optimum, but you cannot tell if it's this one. The only thing you need to know, you need to have to use these methods, is a way to actually evaluate a solution. So if you have several solutions, you need to be able to tell which one is better and which one is worse. So this is typically something you can tell if you have a schedule, then the one that's the shortest, let's say. If you have this glass cutting problem, the smallest the drop of the better the solution. So in the first stage of the algorithm, you remove some subset of worst solutions. Later on, you do the crossover, so you create pairs of solutions and use their genotype, or actually the pieces of the solutions, to create another correct solution. Using this crossover operation creates a new solution, and later on there is also an operation of mutation defined to slightly modify the new solution. It is done from time to time with low probability, just not to have a closed population which will never generate anything from outside. So the algorithm is as simple as this. These few lines of code is what you need. You need to define the selected function and the transform function and the stop condition. Once you have this, this will work. That's why people love it. That's just very little to put into it to find out what to get kind of optimal or just good solution. All right. This is the version which you can probably find on Wikipedia. So it's as any very well-known algorithm has some drawbacks. This one has quite many. It is inspired by biological evolution. However, it is sequential. So you do not have interactions like in real population from time to time between in randomly selected moments of time. You don't have actually the method to get out of local minima, which is the probably biggest problem. If you have two solutions located in a local optimum, which is, let's say, over here, then it will take a very long time to get out of this this local optimum and find the global one. Typically only using mutation operations, so actually randomly selecting something different. So these problems were the basis of our research and our implementation, which we finally did in Erlang. I will get to Erlang in a moment. Okay. So we have we have agents, we have evolution. We created something called Age. This was an idea of how to use the agent paradigm to overcome the drawbacks and the problems with this classical evolutionary algorithm. So we define, as simple as that, a solution agent. It will be now not just a vector of numbers or something like this, but this will be an autonomous being, let's say. We define a set of these agents, so we have a population of agents, and we can define their behaviors, what they can do. They can meet, they can multiply, they can die, and we let it live. And we shall see what happens, right? So we need it asynchronous. The problem is that if you want to do this in non-synchronous way, without stopping and seeing who's good, who's bad, and removing those bad ones, so without any points of synchronization, you need to, well, solve the issue. You don't want to them to stop and tell some central system who should die and who should cross over again. So we defined something called energy in the system, which is split between the agents. So each agent has some amount of energy, and depending on this energy, the agent can do particular things and can't do the other. And the operations, the interactions between agents cause the energy to pass from one agent to another. And in such case, we have the first most significant difference. We have varying number of agents in the population. In classical solutions, you had just an array of them. And the only assumption is that total energy is constant, so that we have some control on this population. It will not explode to infinity, or it will not die out. In such case, we also define a solution on how to overcome the problem of local minima. And we found something bio-inspired again, so we defined this concept of islands. This is actually this same thing done several times for different populations. So we have an evolutionary algorithm running in parallel, actually with very small interaction between one another, but from time to time one agent can just learn how to swim and get to another island. So they can migrate. And this actually solves very well the problem of local minima, because if these two islands are in a local minima and the global optimum is somewhere in between, then if one agent moves from one island to another, it may eventually find the better solution. Okay, so the algorithm was as follows. Each agent independently and autonomously and in parallel decides what to do based on energy. So if the energy was high, the agent could reproduce. And the reproduction caused passing some energy to the new agent. So the newborn agent had some energy as starting point. If the energy of agent wasn't high enough to reproduce, the agent had to fight for energy. So had to find another agent and decide which one's better, simply calculating fitness function, and then some piece of energy was transferred from one agent to another. And once the energy was reduced to zero, then the agent simply died. So it was removed from the system. And there was an action of migration with very low probability as the action of mutation of new agents. Okay. So this was like maybe 10 years ago or 8. And we implemented it, in Java. And this was the small improvement in what we had in a sequential version. So it was impossible to implement huge population of autonomous and concurrent agents in Java because of Java. So we only implemented islands as fully asynchronous. So inside an island, this was still almost sequential algorithm, but going along these rules I showed you before. And the islands just evolved according to the CPU power applied to a particular Java thread. Okay, so this gave way better results than the classical solutions for many benchmarks we did, but that was still not what we wanted. We wanted to have it fully asynchronous, and the only way we could do it without wasting our life waiting for the results was in Erlang. So that's where the Erlang really solved the scientific problem, and nothing else couldn't actually at that point. So we made the implementation where each agent, each solution was an Erlang process. And these Erlang processes decided what to do when they had their CPU time. And the scheduler actually decided somehow which agent could take the action when. So we somehow passed to the scheduler decisions on what will happen next. So we didn't have any point of synchronization in this implementation. To implement this in practice, we needed we needed a method to meet two agents. Agents need to meet to reproduce on the right side and to fight on the left side. So we defined the 4 processes of fight, death, migration, reproduction, and each agent, once it had a time to decided on based on its own energy what to do. So if it wanted to fight, it sent a message to the fight process that it wants to fight with information about its energy and its fitness. Once 2 agents applied, the fight was conducted and the messages were sent back. Which one survived, which one got energy, which one lost energy, and once the agent noticed that his energy is 0, it simply sent a message to the death arena to remove it from the system. The migration arena, quite obvious, and the reproduction arena could create new agents by the reproduction operation. Okay, so actually all the computation was done in the processes themselves, because what costs here is messaging and calculating fitness function. I know that Erlang is not well suited for computation, but it turns out not to be the biggest of our problems. We had a rather simple function, which I will show you in a moment. So each agent, once it was created in a process of reproduction, the first thing it did was calculating its fitness. Once it knew its fitness, it could send this fitness to a fighting arena to decide whether it wins, well, conquers someone or not. So the computation was quite distributed here, and the messaging is what's left. Okay. So talking about local minima. This kind of function is what we took as our benchmark. This is quite simple restricting function. There's the equation. The a is assumed to be 10, and the x changes from -5 point something to 5 point something. The thing is that you don't have a strict definition of number of dimensions. So this is the actually a 2-dimensional one, and we tested it on 1,000 dimensions. You can have as many dimensions as you want. So this optimization problem gets kind of complicated in such case. We tested it on 64 islands, so 64 simultaneous evolutionary algorithms because of hardware we used. And the hardware we used recently was the one node of our supercomputer in computational center in Krakow. We have a Zeus supercomputer which has 25,400 something cores, computational cores available. These are not uniform cores. There are some GPU cores, some FPGA cores, and about 17,000 of general purpose CPUs. And the single node of this computer is 64 core of, I think, eight CPUs. This is one hardware node with as much memory as you may need. Okay, so we ran it on a 64 cores, getting actually what we wanted. So we got new evolutionary algorithm, which is better than we used to have. This might be a bit of a confusion. There are results for 8 to 64 cores. These tests we ran on a hybrid and concurrent version. The concurrent version is this fully concurrent solution where each solution was a process. The hybrid version is the sequential islands version. So if you had a hybrid 8, this was 64 islands calculated sequentially, implemented in Erlang, on 8-core machine. And this diagram shows number of reproductions, so number of new agents, new solutions created, and the fitness of solutions. So how many new agents have to be created to get the solution you want? To make it a bit more clear, I will show you just 2 of those curves for 64 core. And what we got here, at the first, the algorithms of hybrid and concurrent are pretty much the same, but at the end, it turns out that this concurrent version can be up to 20–30% better, which is quite significant. This algorithm behaves totally differently than the sequential version, because Erlang provides something like fully concurrent evolution. This is the only way we could do it in a finite time. And actually right now this solution is presented in Australia on Evolution Computation conference when it got the award of the best paper. So this is something big in the evolution world. In the Erlang, well, yet another application of this tool, this great virtual machine, to something totally different. We like the way it works, but we also found a huge issue here. And well, this is the issue. This is the reproductions per second, depending on the number of cores. On our 64-core machine and non-tuned EVM 16 something, we have the improvement. So it scales up until 48 cores in a concurrent version, and in hybrid version until 40 cores. Above that limit, we have a reduction in the total number of reproductions, in the total performance of whole system. So we are adding more cores and we are getting lower performance. I'm glad to be here to discuss it with the guys implementing the EVM, what's going on. I know that there are tests on this kind of machine. This is quite unique because this is a uniform machine. This is not a distributed system. You can have Erlang on 100 of nodes, each 8 core, and this works. But on a system with 64 core, this is what we are interested in paraphrase. This kind of doesn't scale as we would expect it to. And well, this must be solved, because if Erlang is supposed to rule the multi-core, then this cannot behave like this. Of course, you probably can tune it. That's what I expect to learn here. But this is not good enough. If you have to tune it to every single application, it should just work, off shelf, and handle this this number of cores and even more, preferably. We kind of think we know what's going on, but it needs to be verified. The problem is with message passing. So if we have a single EVM, then the messages are passed in a blocking manner. So once the message is sent, the whole virtual machine freezes for a while of copying memory. If we have 64 core, this is lots of core to stop for copying memory. I need to confirm it with guys implementing it, but it looks like this is the reason. Okay, further steps we are planning to do. We have to implement paraphrase patterns into this solution of ours and make it more general to solve many different problems. Of course, this function I showed you is just a test bed. We have tests with many different functions, and of course some more real-life scenarios like the job shop problem and this glass cutting and things like this. So we are aiming at some real-life applications as well, but first, well, we need to develop tools, develop methods. That's what we're responsible for. So that's the aims for future, and we'll definitely work on this. And we hope to get really nice Erlang tools at the end of Paraphrase. So I encourage you to check what's going on in Paraphrase project. You can have very nice design patterns which you use in one single line of code, which will do all the concurrency for you. That's the aim. And we are working hard to make it work this way. Okay, that's it. Thank you very much. And
thank you.
If you have any questions, I will try to answer.
Well, before I head over the tons of questions, I must say it's really nice to hear that not only companies can build their products on Erlang and be sold for thousands of dollars, but also that papers written in working with Erlang in new communities can get best award papers in other conferences outside the Erlang community.
Hardly a product yet, but
sadly you won't get thousands of millions of euros in research. But
yeah, I was wondering if you find that Erlang is suited for as a general framework for implementing agent-based simulations and so on, in a more broad term? I mean, now you've made one kind of implementation.
Definitely, we're not limiting this implementation only to this kind of evolution. We are building a system out of some blocks, and it will be available for different applications, different agent-based simulation. Actually, we're working on simulation right now as well. And I think Erlang is kind of good for that. The problem is that it's not very efficient in computation. So if you want, this is something that often happens in agent systems, at least those we are working on. So if you have computation-intensive applications and some agents in it, that's probably not the best choice. But if you want to have a massive multi-agent system, it should work rather nicely.
Right, but you showed that it has some improvement over, was it Jade?
Over Jade, some improvement, a few orders of magnitude.
Okay.
But this is not fair, this comparison, because in Jade, once you create an agent, you create a system thread. It's obvious it will be a slow operation. You are creating data structures to initialize this agent. You're creating several behaviors, several hooks in different places of the system. This is very heavy operation because these agents off-shelf offer many services. They register under a name in some global and local registries and prepare some knowledge base and stuff like this. So they are just not suited for very simple operations.
Right. So it has an improvement in terms of process creation mainly. Erlang is faster to create processes.
Definitely.
Yeah, I see.
Yes. It's probably 3 orders of magnitude faster. So if you need something lightweight, like we do here, these agents are primitive. They have a vector of numbers. They perform computation once to calculate the value, and then they just match their energy to some rules and send messages to different processes. That's all they do. There is no AI inside a single agent over here. There's hardly any algorithm. There is just one computation, one function call, and then just one pattern matching, and that's all. So in this kind of application, the Erlang is perfect. This is.
Can I have one more question? A short one. That you showed that it improves performance for evolutionary algorithms. Have you made some performance with other search algorithms, like
not
random
yet?
Trees?
Well, we didn't compare it yet, and in most cases, in other search algorithms, you have to design the agent system to do this search. Over here, we spent some time to find out how to define an agent system that will implement evolution. We come with this energy, this distribution, the energy passing, and these rules for that. In other algorithms, optimization algorithms, you need to find out how to convert sequential optimization of whatever kind to an agent system, to fully concurrent implementation, which will not have any synchronization points, because that's the aim. Oh, it's quite a hard task, but it kind of works, so we'll probably try.
Yeah, very interesting work. I have a question regarding the evolutionary algorithm. So as I understood, you're applying the fitness function to individuals, whereas there's a theory that in natural evolution, the fitness is more attached to the gene. And some people say that this is actually also the reason that there is death by age in higher animals. So they wouldn't compete for the energy with their own offspring.
Yeah.
Is there a concept of an agent dying of age in these types of algorithms?
This could result in getting worse scenarios, worse solutions instead of better solutions. If you found a good solution, you want to keep it, and you want to find even better. And if you kill this good solution, then you will just be left out with something that evolved out of it, but it's worse.
If you kill it before reproduction.
Excuse me?
If you kill it before it has the chance to reproduce.
Well, but the reproduction does not necessarily mean that the new solution is better. In most cases, it will be worse. So in really most cases, you know, this diagram over here shows the number of reproductions in this process. This is in hundreds of millions of reproductions. So this process takes a while to finish, even though this function is pretty simple to calculate. So we have computational power. We do it this way without getting into.
I was just wondering because that's the way it works well in nature.
We actually considered it once, but well, you have to pick some from the nature. It's not necessarily true that our generation is better than the previous one.
Yeah, true. Thank you.
I wonder how does this perform compared to doing it in like a low-level language, like just writing a genetic optimization algorithm in C or with in R or whatever? Is it actually performing better, or is it?
You know, the point we're trying to make here is not about the actual time performance, but about the quality of algorithm. How many reproductions does it have to make to get the solution, get the proper solution? And over here, you don't have time, actually. You don't have, don't know how much it took. Actually, looking at this diagram, you can see that sequential version in Erlang is almost twice as fast in the number of reproduction generated, right? So it will work faster, this sequential one, so far. Because we have overhead of creating new processes and of communication, if you don't have it, you simply calculate the fitness, that's all you do. And over here in this blue implementation, you have to send all those messages and handle creating processes, handle memory by EVM and so on. So we don't know how good could you implement it in C or in assembly, but that's the point here is that we introduced a new algorithm, fully asynchronous one. You probably could do that in C, but this was be rewriting Erlang in C, right? Once more.
Okay, thanks.
You introduced the concept of islands, and you also said that the energy of the whole population is constant. So then the islands themselves, they have the sum of the energy of the agents living there. So different islands have a different energy in total. Did you do anything based on the most fit islands? Well, like
even a high-energy island can be in a local optima, not a global one. And what's interesting in this algorithm is that island can die. Yeah. If every single agent on this island goes down to 0 and the final agent will migrate out, then the island remains empty. And of course, a new agent can come to this island to see what's happening there, just finding no one. Well, it will simply lock waiting in one of these arenas and wait for someone else to come to this island. So this can happen. Measuring the quality of islands, this was also one of the ideas, like the people from Poland right now migrating to UK, right? Why they do it, and will they create better children in UK? That's actually the sort of question. So. The idea behind it is simply to have several algorithms run separately and from time to time just try to mix them. So currently we do not evaluate islands as a whole.
Any other question? Well, thank you very much.
Thank you.